70 million more people show up in the United States in the next 20 years, and increasing density in our cities and urban core. About 1.5 million people per week move to our urban areas as a way to give you an idea of the length of scale here. All this population growth is more congestion and more emissions. Around 3 trillion passenger miles are traveled each year, and 11 billion tons of freight are being moved. For scale, that's the equivalent of 6 million round trips to the moon for the miles and 40 million fully loaded Boeing 777 aircraft, if you want an idea for the weight. So unfortunately for us, they all tend to want to move around at about the same time each day, and they always want to use the same roads. So this results in congestion that costs the average American driver about $1,300 a year in lost time, or about $300 billion to the U.S. economy. And obviously, in addition to the economic drains, there's direct cost to travelers. Transportation is the second highest cost for U.S. households, behind only housing. U.S. households spends an average of about 20% of their income on transportation. So, and despite all these challenges, this transportation is still fundamental to our way of life. Our jobs, our education, healthcare, business, productivity, all of transportation makes all of this possible, and it's the reason why VTO cares. Next slide, please. So I think you might have to click one more time, I think. Yeah, there we go. So the demands on modern transportation have resulted in a complex new world of mobility. The cloud that's showing up on the screen is a bunch of future mobility buzzwords that you've probably heard or seen in the transportation news. The big buzz is around automated, connected, electrified, and shared vehicles, cabs, ACEs, however you want to call that. The idea is that these vehicles in this ideal world will communicate with each other and the transportation infrastructure to ensure we all get to where we're going safely and more efficiently than we do now. But that's only part of the puzzle. You know, we have a current transportation infrastructure, and it's not going to go away anytime soon. There's a lot of new ideas for mobility, like scooters and e-bikes, that are gaining popularity in some areas of the country. And obviously, we're not just moving people, as I alluded to in the last slide, we're moving freight as well. So how do we make this future transportation system more efficient, cleaner, and more accessible to people of all economic backgrounds? And if you're looking at this word cloud and saying, how am I going to make sense of all this? You're really not alone. Making sense of this cloud of ideas needs a systems level look at transportation, and DOE is already working on this, as you'll hopefully see in the next couple of minutes. So, next, please. Get hung up, I think, maybe. This is, there we go. DOE conducts much of its transportation research to the office for which I work and through which the Clean Cities program is supported, the Vehicle Technologies Office. The Vehicle Technologies Office's vision is shown there on the screen, and it's fairly simple. We want more transportation choices that include more efficient technologies when and where they're needed and provided in a way that's more affordable. And everything we do, all the research we do is fitting within that vision. If you click again, please. So VTO's research is really looking not just at vehicles, not just at components, not just at systems, but all three of those, and trying to cover a number of technology areas, as I'll talk about on the next slide. Next, please. So the Vehicle Technologies Office structure is shown here on this slide. We have extensive research efforts for vehicle components and systems with an eye toward increasing the efficiency of both individual vehicles and the overall transportation system. I'm not going to go into great detail on these, as you can find a lot of this information on our website that can describe it much better than I can in the time I have allotted. And certainly you can contact me if you have other questions. But in general, we cover batteries and electrification, electrified vehicles, advanced combustion systems and fuels, conventional and new fuels for regular internal combustion engine vehicles, materials technology to make vehicles lighter and more fuel efficient, and then the transportation systems, which is the energy efficient mobility systems we're going to be talking about a little bit later today. And technology integration is where we move those technologies from research to the real world through our Clean Cities partners. Next, please. All right. So on the last slide, you heard me mention VTO's EEMS programs and its system level view of transportation, but right now it's just, to a lot of you, it's probably just another government acronym, and Lord knows we're good at doing that. Take a couple of slides here in a couple minutes to translate what EEMS is and what it means in the real life and why we care about it. So if you click again, please. So for some people, cheesy animated science fiction is what EEMS means. If you don't know what these characters are, Google's your friend. I'll give you a second to Google that to figure out what those are. If you click again, please. On a more serious note, EEMS can mean a lot of things that are all of interest to VTO. It can mean things like connected automated vehicles for freight, like the truck on the left from Volvo. That is a cabless truck. You know, obviously, because it doesn't need a driver, it can be redesigned in a rather striking way, but still made up of the familiar semi-trailer that's in use all over the world. The middle is a passenger transit pod that some people are already looking at and already testing. And then on the right is individual connected and automated vehicles, some of which who, like the Volvo truck on the left, are taking advantage of connectivity and automation to make the vehicle look considerably different than vehicles do right now. Next, please. An interesting twist on conventional vehicles designs aren't all of the EEMS story. If you click one more time. Micromobility, which is there we go. Micromobility is a broad category of scooters, docked and dockless bike share, and all those other things that you tend to trip over on the street in an urban area, is becoming increasingly popular for many city first mile, last mile trips. Since 2010, people have taken about 207 million trips on these bikes and scooters, with a dramatic increase in trips in recent years, as you can see there. As of the end of last year, 2018, I think? 2018, yeah. E-scooters were available in about 100 US cities. These things have energy and congestion effects that are both positive and negative, so this is something we're interested in. And this is an area where obviously some of the recent pandemic has affected these in ways that we can't quite quantify yet, but we're certainly looking at it. So if you click twice. Excellent. So it's not just moving ourselves around, moving up all this e-commerce stuff that we expect on our doorstep right when we need it, particularly now, is also important. So as you might expect, all of our single-click purchases of diapers and coats and cat figurines and all the rest of the stuff we get on Amazon or wherever else you get stuff from is greatly increased the overall number of packages being shipped to our homes and businesses, as this graph shows from the Postal Service. Some of these e-commerce purchases replace some smaller supermarket trip, but many don't. And the overall impact of all these buying habit shifts on energy and congestion is something we'd like to understand. Click twice again, please. That's not to say that hauling ourselves around is unimportant, because that's changing too, particularly for our longer urban trips. The advent of shared ride services, which we at DOE call transportation network companies, TNCs, ride hailing. You can fill in your own provider, whichever one you might use, has resulted in a drastic increase in overall hailed rides, as you can see on the graph, but a decline in conventional taxi rides that have been an important transportation mode in cities for many decades. The upside is that these TNCs are providing service to areas otherwise not served by taxis, particularly in lower income areas, but recent studies have indicated that TNCs have added to urban traffic in some situations, not subtracted from it. One study we've seen says that about 7% of vehicle miles traveled in the urban core of Washington, D.C., and 13% in San Francisco was from these TNCs. So 2 more clicks, please. And finally, we have to overlay cars, freight trucks, and all the rest of this stuff onto the transportation infrastructure network in this country, which, as many of us know, is not in a particularly good shape. Traffic congestion costs Americans billions of dollars each year in lost productivity and wasted energy, as I alluded to on the second slide. One thing to call your attention to on the picture there is that the annual hours wasted per person ranges for these top 10 cities from 116 hours in Portland to 164 hours in Boston, or for scale, that's like a full-time month of work. So for every 12 months of work you do, you put in an extra month of work just getting back and forth to work. So that's something that we're also interested in understanding and doing something about. So click once more. So if you take one thing away from the last 2 slides, it should be that we're really trying to cover all the new mobility technologies and their associated benefits and challenges, and doing it as part of a systems level process. So next, please. So the opportunity space for mobility is much larger than any one organization, even a big one like DOE can tackle, and requires coverage across a number of disciplines. We have convened 5 of our national laboratories, as shown on the slide here, doing transportation research, and a number of very talented transportation scientists and engineers to build what we call the Smart Mobility Laboratory Consortium, which is a multi-year, multi-lab collaborative dedicated to understanding the energy implications and opportunities of advanced mobility solutions. As it shows here, we've got 5 national laboratories and 5 focus areas. The first focus area, vehicles, are the focus of the Connected Automated Vehicles work, which identifies energy, technology, and usage implications of connectivity and automation, as well as identifying efficient connectivity solutions. People are the main focus of the mobility decision science pillar, which is working to understand the human role of transportation systems, including travel decision-making, as well as technology adoption in the context of future mobility. We cover freight in the multimodal freight transport topic, which evaluated the evolution of freight movement and considered the impact of new modes for long distance good movement and last mile package delivery. The broad transportation environment is covered by urban science, which sought to understand the links between the transportation network and the urban built environment and the potential to enhance access to economic opportunity through improvements to transportation. And finally, we cover fueling in the advanced fueling infrastructure pillar, just looking at the costs, benefits, and requirements for fueling and charging infrastructure to support these systems. In this case, in smart mobility, we're focusing mainly on electrification. Next, please. So on this slide, I'm going to talk for a few minutes. There's a lot of stuff on this slide, discussing some of the findings from each of the research focus areas. Smart 1.0 has just wrapped up last year. A lot of information being produced. Comprehensive final reports are about to be published. And certainly our TI team will make sure that the Clean Cities Network is informed of these findings so we can pass them on to you. So in the first pillar, connected automated vehicles, we were looking at a number of scenarios for connected automated vehicles, various ways they could be adopted. One of the things we found is that in the Chicago metropolitan area, which is one of the models that we've used, 50% uptake in personally owned, highly automated vehicles could increase vehicle miles traveled by up to 25%. Increasing highway congestion and reducing system efficiency. This results in greatly increased unloaded vehicle travel, with roughly 1 out of every 7 vehicles in the system at any time being empty. And you can imagine why. An automated vehicle is probably something that's going to cost you a lot of money. So you're going to want to take advantage of that as best you can. So the first person going to work is probably going to take it to work and send it back home for the next person to use. Mobility decision science, we've already come up with some interesting findings on how consumer behavior affects transportation. We found that e-commerce deliveries can certainly replace shopping trips, but can also increase the overall amounts of goods purchased. Our analysis indicates that about 37% of the items received via delivery would not have been purchased if delivery had not been available. And I'm sure you can think of something you've bought on Amazon that you said, well, what the heck, if it's going to come up on my doorstep, sure, I'll buy it. And obviously these additional deliveries lead to additional trucks on the road and additional delivery miles traveled. Broadly speaking, one might ask the question of whether e-commerce deliveries are going to substitute for household shopping trips or simply add to those, and the short answer is yes, it'll do both. What we found is that between 55 and 70% of deliveries are fully substituting for a shopping trip, while 20 to 35% fully supplement a shopping trip depending on what's being purchased. And those of you who are astute will notice that there's about 10% in the middle that's neither fully substituting nor fully supplementing, which gives you an idea of the polarization of how people are shopping. Respondents revealed that they rarely purchase groceries or prepared meals via e-commerce, at least at the time we did it. It's probably different now, but are more split when it comes to clothing and household items. Since groceries are something that's very commonly purchased, it's important to know that these personal vehicle trips are unlikely to be replaced by e-commerce. Moving on to multimodal freight, given the complexity of freight in this country, it's not surprising that they came to the conclusion that freight is complicated. We move a lot of stuff to a lot of places and use a lot of different vehicles to move the stuff, so there really aren't a lot of simple answers for making freight more efficient. One of the things we've been looking at is interesting new freight modes like package drones that you've probably seen a lot of press play recently. One of the things we found by testing these drones is that on a per mile basis, the energy consumption of these drones is not a whole lot different than that of a light duty electric vehicle. And although these drones don't necessarily save energy on a per mile basis relative to regular land-based conventional modes, they can potentially save overall energy by reducing the total number of miles by traveling a straight line instead of using the roads, and eliminating traffic delays from traffic signals and congestions and things like that. And another thing we found is that although e-commerce is generating a large increase in last mile delivery, it can result in an overall net reduction in vehicle miles traveled of up to 50 or 60% and energy use of up to a third. And that's due to the trade-off between fewer shopping trips at 7 to 8 miles per trip for you and me, balanced against more deliveries, which adds roughly about 0.4 of a mile per each added stop for these these delivery companies. That's what makes the difference. So, moving on to urban science. The urban science folks have created a new metric for transportation efficiency that's trying to capture the energy, time, and cost impacts of regional travel. This metric, which we talk about as mobility, energy, productivity, or MEP, looks at the ability of people to access job, shopping, and other opportunities across the transportation modes available to them. I got a couple of slides coming up on that, so I won't talk about that more here. Some of the other work that the urban science folks have been doing is exploring the challenging urban problem of optimizing curb space use for competing transportation modes. Curb space is a particular issue for cities, as so many transportation modes demand the space. TNCs and deliveries and people parking and people walking and bicycles and motorcycles and all the rest of it. The team is looking at some algorithms and analytical tools to help urban areas find the right balance of accessibility for all these modes. Another thing that we found is that, at least in our modeling and simulation, in a hub and spoke transportation system like Chicago has, there's an opportunity for ride hailing and transit to be complementary, with transit being a key mobility provider in the urban downtown and ride hailing providing personal mobility in the suburbs. This shows that ride hailing doesn't necessarily always take ridership away from traditional transit, as some have certainly feared. Finally, advanced fueling infrastructure found that infrastructure planning is really all about trade-offs and how you quantify those trade-offs of what kind of level of service do you provide for EV drivers, for EVSE, the cost of such infrastructure, and how much EV mobility you get from this. One of the things we found is that for ride hailing, car sharing vehicles, and other commercial EVs operating in a small geographic area, in this case it was a Seattle car sharing study, increasing charging power above 50 kilowatts for a DC fast charger will have a greater effect on minimizing charging trip downtime than adding more charging station, because charging time is what usually dominates the amount of time and not you looking for another EVSE. So next slide, please. So we've tossed around the term mobility quite a bit, so it's probably important that we agree on what mobility means, at least what DOE thinks it means. And you know, if we want to improve mobility, how do we know if we're successful? Surprisingly, at least surprisingly to us, maybe not surprisingly to urban planners, there are no existing mobility metrics that serve the needs that we have, and current transportation metrics that we can find tend to focus just on utilization of the road network. And that's not all we're interested in. We want to look at the multimodal approach to connect people to the things they need, while at the same time minimizing energy consumption. So the way we've been defining mobility in EEMS is the quality of a network or system to connect people to goods, services, and employment, really the things that define a high quality of life. Next, please. So if we define mobility in the way I just described, then we really need some way of quantifying that mobility so we can see how we've improved it. A mobility metric would account for the energy, cost, and time factors of mobility. MEP, or mobility energy productivity metric, which I alluded to before, is what we've developed to address those three: time, affordability, and energy aspects. This metric scales geographically, so it's useful for evaluating impacts at a corridor, neighborhood, city, or regional levels. It also allows us to incorporate different modes beyond just the automobiles that have dominated cities' designs and land use patterns for many years. And it not only focuses on energy, which obviously we're interested in as DOE, but also time and cost, which are important factors for travelers. The idea behind MEP is that we're trying to quantify the number of opportunities that people can reach within a certain travel time via different transportation modes that are available to you. Realizing this is a little bit arcane, we'll talk about an example in the next slide. It'll probably make a little bit more sense. We weight the opportunities measured by the time, energy, and cost efficiency metrics of different transportation modes, as well as how frequently you engage in these different types of activities. So conceptually speaking, you might think about a high MEP situation as a high-rise mixed-use building in New York City, Manhattan. You probably live and work in the building maybe, or you live and work close by to your building, and probably everything you need shopping-wise is on the same block, so you're using a very efficient transport mode, i.e. walking, to get to every location, and you don't have to travel very far. Somewhere in the middle would be typical suburbia. There's a lot of job and shopping opportunities near where you live, but these are all reached by a relatively low efficiency mode of transport, the car, which is lower efficiency, the transit, biking, or walking. And then low MEP, you might think of that as a rural area where the main employment, shopping, and services are many miles away from you, and really you can only get there by a car. So see. Next slide, please. So just a way to illustrate what MEP means conceptually with pictures, because I find that always helps me understand things a little bit better. This is based on the city of Columbus, Ohio. Columbus has been a good partner for us because their smart cities effort has produced a lot of the kind of data that we would need to create these kinds of models and create this kind of analysis. As you can see by the baseline map on the left, we really only have MEP scores that are fairly high, i.e. the ones in green, right in the urban core where you'd expect them to be in a modern city where there's a lot of walking, biking, or transit, and people have a lot of places to get to in a relatively short area. So asking the question of what if you triple the fuel economy of vehicles, increase them by 200%, and change nothing else in the city of Columbus, and you get the map on the right, which shows that the MEP score has increased for basically the entire metropolitan area because we've only changed the miles per gallon of vehicles so people can still get to the same places and the same opportunities at the same distances, travel times, but with much more efficient cars. And you can see by the number at the top that the city level MEP goes up. So it's kind of a what if scenario. What if we improve transit? What if we improve bike share, things like that? So helpful tool for us to help explain the metric, the dynamics of transit and transportation in a city and in ways that are fairly graphical. So next, please. So the research work that VTO that we're doing with our partners is not really all that valuable if we just sit it on a shelf and say, gosh, what a great job we did. So EEMS and TI are both working to get the results of the research out to the broader community. On the left, and Ben alluded to this in his slides, is the alternative fuel data centers. We have a page on transportation system efficiency, some high level information, some links to the DOE EEMS sites and some other resources. And understanding the important role of the Clean Cities Coordinator in our network, we've created some more specific resources available just to our coordinators to help them be better knowledge about all of these things. So basically, these are designed to build up our coordinator expertise in new mobility to connect with peer examples and technical knowledge. So we have some plans to expand this even more with some additional case studies. Next, please. So looking at how this translates to the Southeast, we realize that our research to date is using some specific local models that we've used because we need a lot of detailed data to drive these models, which is basically we've had this information. We're working on ways to characterize cities at a detailed level so that we can then use what we found in Chicago and San Francisco and generalize them to cities throughout the rest of the nation. Also really looking at how we can use our tools and our models and provide some simpler tools for localities to use on their own in studying mobility in their regions, and obviously sharing information and broad conclusions nationally through the Clean Cities Network. And obviously we are certainly open for you to contact us if you have some ideas on how to collaborate. So next, please. So the future of mobility is still bright, wrapping up. Even with the current situation, we feel like in a pandemic world that there are opportunities to make our transportation system better. Consumer mobility behavior will be the key in getting to this efficient and safe transportation system. We need to understand how people are making their choices and what would motivate them to make better choices. The Vehicle Technologies Office is working on those problems, as hopefully I've demonstrated over the last few minutes, with the tools, resources, and insights to help all of you with this new mobility world. And Clean Cities coordinators are your regional connection to all of DOE's VTO researchers and technical expertise. So really don't be shy about reaching out to Ben or to your local coordinator to tap this valuable resource. And they're here to help, and so are we. So, and the next one should be the last one. All right, and that wraps it up.
Thank you, Michael. All right, we're gonna transition over to Ronnie's presentation here. Just 1 second. All right, Ronnie, you are good to go.
I think this is the last slide, so we'll go to the first slide.
Oh. Ha. You got me. All right, there we go.
Thank you. Thank you very much. Thank you for inviting me to this webinar. So I'm Ronnie Chaudhary. I'm the Director of Center for Connected Multimodal Mobility. Today my talk will be on energy conservation research using future transportation technologies. So yeah, so next slide, please. So first I'll touch on some background about our center. Our center is an innovation center. Our goal is to transform multimodal mobility through connectivity, like wireless communications or wired communications, and using data analytics. So it's the computer science aspects of data, is the big data, infrastructure, analysis of big data, use of AI. So all are included in data analytics. And the next is through automation. So autonomous vehicles, autonomous drones, autonomous trucks. So automation, robotics is another thrust area of our center. And wrapping everything up, the technology side of it is cybersecurity and privacy. So we are looking at these advanced systems, future technologies, wireless communication, infrastructure. So how we secure them from cyber attacks. So that's also a major focus of our center. Next slide, please. So our center, this is our center makeup. So Clemson University is the lead. And then we have Benedict College, the Citadel, South Carolina State University, and University of South Carolina. So these 5 universities in South Carolina are members of the C2M2 consortium. And we do research, we do education training, and we work with different community organizations, with public agencies to advance the economic development. And also another aspect of our center is diversity and outreach. So we have several activities every year we do through our diversity and outreach program. The next slide, please. So this is what we are doing now. So we actually fund research projects. So from these 5 partner institutions, so we invite faculty members, researchers to submit proposals, and we go through a peer review process, and we select projects that the reviewers think should be funded. So we have 4 major projects, the foundational projects. So this is based on the testbed we have at Clemson University. We have a connected and autonomous vehicle testbed. So we are developing infrastructure for future autonomous and connected vehicles. So that's a part of the foundational project. So we look at big data analytics, cyber physical systems, and then information aware automation. And then the last is cybersecurity and privacy. And then the other projects, the 24 projects, it's divided between the 5 universities I just mentioned. So we're looking at different modes. So it's truly a multimodal effort. So we look at automobile, freight, shared mobility, pedestrian, bicyclist, vulnerable road users, scooter users. So everything are included in our center's projects. And so we look at safety, mobility, and also energy and environment. So we have several research currently ongoing on the energy and environment side. So next slide, please. So first, I would just like to first introduce a federal resource for energy use in connected autonomous vehicles. So this is from the ARC-IT, the National ITS Reference Architecture. So if you go to this page, the website address is just on the right top corner. So you can find a lot of information about the different applications that can be achieved through connected autonomous vehicles. So here's some examples. So with dynamic transit operation, dynamic eco-driving, I'm just reading some examples, eco-traffic signal timing. So all these eco-driving aspects of it and environmental aspects through which we can achieve sustainable transportation are included on the different applications that are mentioned, this website, it was developed by USDOT. It's a great resource, a great starting point. When I do any research on any connected vehicle applications, first I look at the website. It has application related to, say, safety. In addition to energy, it has application related to freight. So, but you can look at the high-level view of the application or high-level architecture. What are the requirements for each of these applications to be realized? So, it's a very good resource for research, and especially for energy research. The next slide, please. So, one question we hear whether autonomous vehicles will be electric. So right now, Clemson University just started an undergraduate major in electric vehicles. Our center is a part of that undergraduate major. So, and we are looking at, from our side, our center side, we are promoting that our autonomous vehicles should be electric. And this slide shows some of the news that from different newspapers and magazines. So they're all promoting or they're validating that we can have the greatest benefit if we have all autonomous vehicles electric. So this is just promoting that, that what I also believe in, that autonomous vehicles should be electric. Next, please. So now this is where our center is coming in, Center for Connected Multimodal Mobility. So what is our expertise in the area, or energy and environment? So what we are promoting, that we have to create a transportation cyber physical systems where vehicles, bikes, pedestrians communicate with the cyber world. So that will make the transportation system more safe, more efficient, more energy efficient. So this is a high level diagram of the cyber physical system. So we have on the left side the digital infrastructure that will support our transportation modes, different transportation modes. And on the right side, you see we are just showing the cyber physical system. So the vehicles are providing data to the cloud or backend infrastructure. And the backend infrastructure is processing the data, data generated by vehicles, by pedestrians, or by trucks, any transportation modes or infrastructure. So for example, it could be traffic signals, it could be for any other roadside device. So all this information is going to the cloud, and or any infrastructure, computing infrastructure. It could be a server. It's processing the data, and after the processed data is then used to control the physical transportation system. So the cyber world is processing the data, and then their data is used to manage and control the physical transportation system. So it's a great friendship between the physical world and the cyber world. So to achieve safety, energy, efficiency, mobility. So this all can be achieved by these transportation cyber physical systems. So that is our thrust area. Everything you'll see, the projects that I will discuss in the following slides, everything is based on these TCPS, or transportation cyber physical systems. Next slide, please. So under these transportation cyber physical systems, we have a distributed digital infrastructure. So for example, on the left, you have the backend infrastructure. It could be a cloud services. It could be managed by a transportation agency. It could be a server at a traffic management center. So it could be an emergency management center. So all those are center infrastructure. So who are managing your highways or any transportation system. And then we have roadside infrastructure. So that is a part of your digital infrastructure. We have, there are some examples. You could have a traffic signal that are communicating with vehicles, and also vehicles are communicating with traffic signal controllers. And then we can have roadside units. So the picture is showing a roadside unit. It is a dedicated short range unit. So it is communicating information to all the vehicles that are connected, and also the connected vehicles are also broadcasting information, and there it is also received by this roadside device. And we can have different types of roadway sensors, like traffic cameras or radar detectors or loop detectors, so that are also communicating with the vehicles. Now on the rightmost side, we have connected autonomous vehicles. So, and the connected autonomous vehicles have sensors, in-vehicle network, the communication network, and also it has it interfaces with external devices through a communication medium. And we have the processor in the car, like a software, so that is processing all the information that are being received by the vehicle. So, and they are communicating. So we see so the roadside infrastructure and backend infrastructure communicating through wired or wireless communication. It depends on what works best. And then between the connected autonomous vehicles is wireless communication, and between the vehicles and the roadside infrastructure is a wireless communication. So there is a big emphasis on wireless communication, and that's also one focus area of our research, our center as well. Next, please. So as I was mentioning in the previous slide, so wireless communication is the key if you want to connect the physical world with the cyber world. So this is very important. And but the wireless communication has to be heterogeneous. So what I mean by that, you don't know what communication infrastructure you will encounter in the path of a vehicle or pedestrians moving from one location to another location. So, but whatever communication option available or technology available, there should be seamless transition. For example, I'm within a zone where I have dedicated short-range communication, but then I move to another area, they have 5G. But the transfer, so your vehicle is moving from an area where you had DSRC to an area where they have 5G. So the transition from DSRC to 5G should be instantaneous. So there should not be any delay. The handoff will be very, very fast. Similarly, if you're in a Wi-Fi area, a vehicle or a pedestrian, and they're moving to an area where you don't have Wi-Fi coverage, you only have LTE. So it will just move to that area. And also this transition, it's not only that that you have, you may have two options available, but it will select what option is best for what the vehicle is trying to do, or what the user is trying to do with the wireless communication. So we developed a software called POSH through our center that can determine that okay, based on the throughput requirements, coverage that are available, what delay, like how much time you need for the application to run smoothly, what are the possible data loss and quality of service. Based on these communication measures of effectiveness, it will select what communication option to choose. Is it DSRC, is it 5G, Wi-Fi, or LTE? And also it is helping you from transitioning from one option to one wireless option to another option. So on the top of that, we are using software-defined networking to make this seamless, the transition seamless. So as we'll see in the following slides, this is very important. We need this HETNet service, or heterogeneous wireless service, to make our energy management application successful. As you'll see, it's all about communication. Next slide, please. Next slide, thank you. So for our energy management, so we are using predictive analytics. For example, we just completed a project for National Science Foundation where we wanted to optimize the energy conservation for plug-in hybrid electric vehicles. So if we can predict the vehicle profile for the next 30 seconds or 1 minute, then we can program the vehicle, connected vehicles, automated vehicles, in a way that if it moves within that programmable energy optimization strategy, then the energy consumption will be lowest. So it will increase the use of electricity and reduce the consumption of gasoline. So, and we use predictive analytics. We use artificial intelligence to predict the future traffic conditions. And this prediction not only works in the case where I did with plug-in hybrid electric vehicles, but it works with a lot of different things for electric vehicle routing, for helping battery electric vehicle generate revenues. So this is at the heart of the prediction for energy management. Next slide, please.
Hey, Ronnie, we've got about 5 minutes left till.
Okay, I will be very quick.
Okay.
And I work in an auction house, so I can be very quick talker. So. All right, so TCPS-based energy management. So the next slide, please. So I'll discuss some of the project that we did. So I'll just say what this is about wireless charging. So we one thing we did with this project is how electric vehicle can generate revenue. So we developed a concept or a model where the electric vehicle can sell power to the electricity grid through an aggregation server. So, and we found that if we implement this strategy, electric vehicle can owner can make about $1,000 or more a year. So this is a nice concept of providing revenue for electric vehicles. At the same time, the grid provider can get the necessary power during a time of high demand. Next slide, please. So this is a dynamic routing of electric vehicles. So it's an in-motion power transfer. So when the vehicle is moving at a full travel speed, it is getting charged. But we used a model to make sure that that the electric vehicle, so there are maybe thousands of electric vehicles in the network, and based on the state of charge, we routed them in the appropriate location where they can be charged through wireless charging. So our objective was to minimize travel time, minimize energy costs, and maintain the state of charge in electric vehicles. The next one, please. So now this slide and the next slide is similar, but here we looked at the wireless charging. So it's we have a global charging controller. It is guiding different electric vehicles through the charging station. And also we included here the opportunistic charging. So there might be more opportunity for electric vehicle to be charged at this intersection because they're staying there for 3-4 minutes or so. So it is just guiding electric vehicles in an urban area. Next, please. Next slide. So this is also wireless charging, but it is doing in a sustainable fashion. So we developed a model where the solar plant, solar power can power the electricity grid, and the electricity grid will then provide power to the wireless charging station on the pavement. And we developed a revenue estimation. So we did an economic analysis with it, so that it's really profitable for the utility companies as well as it's useful to the electric vehicles. So it was in addition to technology evaluation, we also evaluated the economics of the system. Next, please. So this is, I was mentioning earlier that if you have predictive traffic information, like the predicted traffic profiles, speed profile, then you can optimize energy in a plug-in hybrid electric vehicles. So, and we found that the model that we generated produces significant benefits to plug-in hybrid electric vehicles with predictive traffic information. And we used artificial intelligence to predict future traffic. Next, please. So now we are talking about for energy management, our vehicles, any transportation system is communicating with the cyber world. So anything that is that are vulnerable to outside attack are also applies to this case to this transportation cyber physical systems. So next slide, please. So in addition to developing models for transportation cyber physical systems, we developed a system where we can protect the vehicles through software-defined networking. So on the left, you see the in-vehicle network, but it can be attacked. So it can attack the energy management system in the vehicle. And then you can see how the attack, the red arrows, the attack is propagating to different systems, the brake control system and so on. Also, it is attacking your energy system, so your energy consumption will be much higher, but it can do more serious damage. So what we did on the rightmost slide, we developed a system through software-defined networking that we can easily we can catch when an attack is made to our vehicle, and then see that in this case the attack was on energy management system, but we can just at the source of the attack we can separate the network, or we can just disengage the network that where the attack is coming from, and then you can have a secure system. And we have done this in real world, and our research suggests that we can really protect our in-vehicle system through the software-defined network security system. Next, please. So we are doing our energy research in our test bed, our South Carolina connected vehicle test bed. So we have infrastructure there. We have the infrastructure I just mentioned, transportation cyber physical system infrastructure. We have DSRC radios. We have our own LT stations, as you'll see on the top of that building. We have cameras. So we have, and we have communication system. We have heterogeneous wireless communication system in place. We are doing pedestrian detection. We are doing energy research, safety research. So now simulation is great, but in order to see whether really it's affecting energy usage through signal coordination or through optimization of different services, so the real world test bed is the best. So we are doing it through our center in Clemson. Next, please. Next slide, please. So this is our tech based on the research that we have done. So we have to really have the optimal benefits, not only for safety or mobility, for energy management. We need to have a digital infrastructure for transportation. So when we talk about that we need a significant investment in transportation, at the same time, I think we need to synergize that investment with digital infrastructure so we can create a true TCPS. So, and then we have to integrate the TCPS with energy infrastructure, which includes electricity grid, which includes the charging stations. It could mean that wireless charging facilities. So it should be a part of your TCPS, because you need to communicate with the vehicles, or the other users need to communicate with this infrastructure. The third point, now communication is the key. So we highly recommend that we need to use heterogeneous connectivity, and the software we developed at Clemson could be a good resource to support such connectivity. So, and then the last point is protect the transportation cyber physical systems against cyber attack. We have developed tools that can do that, but it's an important that you need to protect the system that is helping to achieve your energy optimization goal. So privacy and cyber attack is are the keys to a sustainable future of our future transportation system. The next slide, please. So this is a quick summary of our center's research on energy using connected autonomous vehicles. And all the projects I mentioned, we have published peer-reviewed papers, journal papers, several papers in each of the topics. So if anyone interested in knowing more of any of this, I can share those papers with you. Thank you.
All right, thank you to our presenters for those both exciting and interesting presentations. I think we have time for one question. We'll follow up with the other questions with our presenters, but Landon, did you have one?
Yes, so we have a question for Michael about DOE's engagement with other ride-hailing companies such as Uber or Lyft to reduce the vehicle miles traveled, and how are these partnerships developing from the federal level, and then how maybe can folks at the local level work with those partners as well?
Thanks. Yeah, I know that DOE has been trying to forge partnerships with Uber and Lyft. I don't know that we have been particularly successful to date. Those companies are fairly tight-lipped with their data, and that's kind of where we wanted to start is to understand where their vehicles are and how they're traveling in order to do that. I think the short answer is we haven't had much engagement to date, as far as I know, but it's something we certainly want to do, and to the extent that we can get help from our local coalitions to do that would be great. So folks at NREL, National Renewable Energy Lab, are the ones trying to spearhead that.
Awesome, thank you.
All right, guys, since we're just a little bit over 4, we're gonna wrap it up, but we're gonna follow up with all the questions in the chat to our presenters, and we'll follow up with everyone who presented with those answers. So I'd like just take the chance again to say thank you to everyone for attending and presenting. Hope you have a great rest of your afternoon, and thank you very much.
Thank you.
Thank you.